In this video, we will be investigating the reason for why tennis rackets fail. Our group chose this topic because many of us played tennis growing up, as you can see with the trophies shown. We want to explore how fatigue loading leads to failure of the racket frame in particular. Another important reason for why we wanted to analyze fatigue failure of tennis rackets was because they are so expensive, making it a hassle to replace them. In order to begin our analysis and calculating the life cycle of a racket frame, we first needed to find the force exerted on a tennis racket by a ball. We used a slow motion video of a person hitting a tennis ball to support our calculations, and assumed that the ball would be served at an average speed of 117 miles per hour, which is common for professional players. We utilized Newton's second law to find the force we needed using values determined from the video. In the video, the tennis ball was in contact with the racket for about 23 frames, so we were able to calculate an impact time of 5 milliseconds by dividing by the frame rate of the video, 5,000 frames per second. We assumed that the mass of a standard tennis ball was 0.06 kilograms, and we were able to calculate the force of the racket to be 620 newtons.
We have the force on the racket strings, but now how do we find the force in the frame? We can assume that the racket frame is a thinly walled pressure vessel, and that the force acts only in the center, and so we need to find the radial and hoop stresses acting on the racket. The radial stress acts perpendicular to the racket, while the hoop stress would be tangential around the inner ring of the frame. Using dimensions found online and equations from Chapter 3 of the Shigley textbook, we can estimate the pressure. Pressure is force over area, where area is a racket circumference times the thickness. And then using that pressure and adjusting the equations for the elliptical shape of the racket, we can find the two stress values where hoop stress is about 400 kilopascals and the radial stress is around negative 45 kilopascals. In order to use these stress values to find the effects of failure, we need to analyze the combined impact, so we use the von Mises stress equation to find the maximum stress value. The minimum is 0 since it's assuming there will be no force on the racket without the ball. Now, to find the factor of safety, we calculate the mean and alternating stresses as shown.
Using these stresses, we can calculate the fatigue factor of safety using the Goodman criteria equation from Chapter 6 of the Shigley textbook. Most rackets are made of a carbon graphite composite material, and finding an exact ultimate tensile strength proved very difficult. Some sources had the value as low as 4.8 megapascals, all the way up to several thousand depending on the graphite and carbon contents. So to be safe, we'll use the lowest value. For the endurance limit, if there were no other external factors, the maximum value would be half of the ultimate tensile strength. With all these assumptions, we end up with a factor of safety of nearly 8. This is very high, which would mean the racket should never fail. So why do they? In reality, the rackets fail because of modification factors that greatly lower the endurance limit. As seen in the Shigley equation, things like temperature, manufacturing defects, and microscopic cracks that could act as stress raisers, also off-center impacts could all lower this limit. As seen in this animation, as we lower the endurance limit, the fatigue safety drops rapidly, eventually less than 1, showing that it would not have infinite life. This would result in fatigue failure and plastic deformation like we see here in this photo.